Hello everybody, welcome to this bonus material for the Parallele Programming lecture at ETH Zurich in 2021, this year online due to Corona. If you're a student of this lecture, I've promised you this bonus material during the lecture, and I was not able to incorporate it during the normal lecture, which has the benefit for me that I can now add it as bonus material only for the interested students. And furthermore, I can even hold it in English because it's not part of the official lecture, and for that reason will also not be part of the exam, of course. So I can choose my language freely as opposed to the normal lecture where I have to speak in German, and as you may have realized, it's for me much more natural to speak in English because I'm mostly thinking in English as well. So now I want to tell you a little bit about one of the nicer proofs that we couldn't do in the lecture, but it's one of those proofs that you will see multiple times during your studies, and you will actually kind of need it for more interesting proofs. So it'll show you two things. One is the actual proof itself, so that atomic registers have consensus number one, but it'll also show you a way to lead proofs by somewhat a mixture of negative proof techniques or proof by contradiction, as well as full enumeration of subspaces, so how to reduce subspaces. So this is what we're going to do today. So what I'm going to show is really, in this bonus lecture, really trying to understand what Hurley and Chavit in their book call one of the most fundamental principles in parallel computing. So this impossibility proofs. Let me just quote from their book. The aforementioned corollary is perhaps one of the most striking impossibility results in computer science. So this was in fact introduced by the authors, so this is what they say themselves about this result. It explains why, if we want to implement lock-free concurrent data structures on modern multiprocessors, our hardware must provide primitive synchronization operations other than loads and stores, in brackets reads and writes. So this really means with this proof we can show the absolute necessity of atomic operations or higher level concepts such as hardware transactional memory in practice. This was a long time debated. This was not really clear whether they're really necessary. It was early recognized that they're helpful, but are they really necessary, yes or no? And this proof shows that for at least weight-free implementations, they are pretty much necessary for any non-trivial parallel program. Because this this consensus problem, as I mentioned in the lecture, is really kind of the simplest possible primitive you have to you can prove things about that you have to use in any non-trivial parallel algorithm. For example, in summation that has a consensus, or distributed summation has a consensus component, and pretty much everything else where threads need to have some kind of common view on the global state. So see consensus not as a practical issue, but really see it as an implementation or something that helps you to understand what the limits of computation are. So I'm not going to repeat I'm briefly repeating the consensus problem, but we introduced this formally in the lecture. So, and as I mentioned, we will talk about weight-free consensus with reader-writer registers. So I want to show you that if you have a system that can only read and write to memory, and this is in theory very often called registers, but it's essentially the shared memory operations that we learned. And if you want to have this, if you want to implement consensus in a weight-free way, that is actually not possible on that system, so you need additional operations how to do this. I showed you in the lecture that a compare and swap operation is absolutely sufficient for this to synchronize an arbitrary number of threads, so basically having a consensus number of infinity. So why do we care about weight-free? Well, I explained this before. It's really that if you have safety critical systems that have to make certain decisions in certain times, like airplanes, nuclear power plants, and brake systems, you better have a weight-free algorithm, because otherwise it could happen that even in a lock-free algorithm that through repeated conflicts, you could have a slowdown that may be not acceptable in your real-time system. So the solution, of course, as I mentioned, are atomic operations, but this is what we already discussed. So here in this bonus lecture, it's really about showing you why it's not possible with reader-writer registers. That's the whole content. So we have this consensus hierarchy that I mentioned. The consensus hierarchy is really the number of threads, or the consensus number is really the number of threads that you can synchronize with an infinite number of objects of a certain type, in our case reader-writer registers, in a weight-free manner for the consensus problem. So this basically means that we're going to show that it has consensus number 1. We have seen that FIFO queues have consensus number 2, and several other operations as well. So I haven't shown this in the lecture, but it's relatively easy to show. You can use a very similar technique to what I'm proposing here, or what I'm showing you in a couple of minutes, to also show the limits of fetch and increment operations, for example. And then with compare and swap, we can synchronize an arbitrary number of threads in a weight-free manner. Okay, so let me get right to the point. Let's quickly recap the weight-free consensus protocol. So we have multiple different multiple different threads or cores that want to reach a common goal. So the easiest, simplest protocol we can have is this consensus, where each of the threads proposes a value. Like in this case, the green processor proposes 23, and there are 3 conditions that have to be met. Is that the returned value has to be one of the values proposed. All of the processes have to, or all of the threads or processes or cores, I'm using this equivalently here, have to return the same value. So it has to be, all of them return the same value. It has to be proposed, and it has to be in a weight-free manner. So after a fixed number of steps, O of 1 number of steps, this result must be returned. And other processes that are essentially missing in action or show up after a very large number of threads of steps must thus get the pre-decided result. And this is by implication. So let me go with the example here. So we have green one proposes 23, the pink one proposes 42. Then comes the green one moves on a finite number of steps. Then maybe the dark green one proposes 34, but now the green one actually returns. So which means the green one must return either 23 or 42 or 34, because it has not heard of the blue one process contribution, so it cannot return that. So it has to return something from the set that is actually known. In this case, it decides to return 23, which then really means that any other process that is now coming or returning after that call must also return 23 and nothing else. And so now that this process contributes 11, plays absolutely no role, because it's now pre-decided that the result has to be 23. Okay, so for all possible executions. And this by extrapolation, we can now basically say if there's a single process that runs without any of the other processes, it must decide its value. And this also means that all the other processes then later, when they call decide in that round, they must also return or decide the value of the process that returned first. Okay, so what we now do is we simplify the problem, because right now here we have arbitrary values like 23 or 11 as input values, and we have an arbitrary number of threads. But since we want to show that something is impossible, we can just reduce the problem and make it easier and still show that the easier instance of the problem is impossible. So in other words, if I show that I cannot synchronize 2 threads or I cannot solve the consensus problem on 2 threads in a weight-free manner, then I will definitely not be able to solve it on 3 or more threads. So I'm just going down to 2 here, and we call this a 2-thread consensus, and very soon we are actually going to binary 2-thread consensus, because that's another simplification. And even for that very, very simple problem, I will show you that this is not going to be possible in a weight-free manner. Okay, so now we have 2-thread consensus. We have only 2 threads here. It's called the green and the red one, and there are now various scenarios that are still allowed. Namely, we can have a large number of different input values that we could have. But let's now go through a couple of scenarios with these 2-thread consensus to get a little bit warmed up of what this really means in terms of what the results or what can happen during this protocol. So here again, in this case, the green one could propose 23, the red one proposes 42, fine, and then the green one says we agreed on 23, exactly like before, and so now the red one would actually have to say 23, but it for some reason says 42, which really means that this is an illegal setup for this consensus protocol. So it would have to return, especially if the previous process already returned 23, it would also have to return 23, because this would be not consistent here if it was returning 42. So it's pretty clear. It also has to be valid, so if I'm proposing 23 and the other one is proposing 42, but for some reason I return, or some of these processes returns 420, that is also, even though these two agree on the returned result, it is not a valid input, which means the protocol is incorrect in this case. Just as a couple of examples here. So it also has to be weight-free, which means if the green process now proposes 23, now the red process proposes 42, and now the red process is just running for a long time, and for some reason or does something else, or is basically not scheduled, so the green process returns, would be up to returning, but the red process is not actually doing anything, it's not making any progress. The green process must return within a finite number of steps, irrespective of the state of the red process. Right? This is what I mean by weight-free here. So meaning that even if the little daemon, the little operating system daemon comes and delays the red process forever, or the red process goes on vacation forever, for whatever reason, the green process must finish in a finite number of steps, even without ever hearing from the red process. Right? This is very, very important. It's going to be a central component of the proof that we're using later. This comes from the wait freedom. Right? Wait freedom says that they have to all finish after invocation in a fixed number of steps. So other processes or threads play no role in that decision. So it's this here again, the wait freedom. Okay, so now let me simplify further. So we simplified to two-thread consensus. I already told you that we are now going one step further and say, well, you know, it's even simpler. Instead of proposing a full integer, we can just say, well, if we cannot even decide binary consensus, where the output is either, the input and the output is either 0 or 1, we can definitely not solve integer consensus. Right? This should be relatively clear. I can actually show you that for two threads, this is equivalent to integer consensus, which means I can implement integer consensus in terms of binary consensus, and I can implement binary consensus in terms of integer consensus. And this is how I show equivalence. If I can implement A with B and B with A, then A and B are equivalently powerful. So, well, how can we prove this equivalence? Well, I just show you an implementation of A and B and B and A. So I show you first that we if we have an integer decider, wait-free consensus protocol, then I can easily implement a binary wait-free protocol, which is now extremely simple because basically a binary is a special integer. A binary is a one-bit integer. Right? So it's either 0 or 1. So which means if I have an integer decision routine, I can just call it with a binary and it'll just be working, because if it works for an integer, it works for a binary, because a binary is an integer. Okay, the other direction, the vice versa, is not so simple, but works with two threads, very, very simple as well. If I now assume I have a binary routine, bin decide, which only takes a binary value, but I only have two threads, thread 0 and thread 1, what do? Well, I instantiate a shared array called propose. I write the input at each of the threads into this shared array, and then I run a binary decide to decide which of the two processes, 0 or 1, wins, and then I just return that value of the proposed process. So this will actually work. It only works in the two-process case, of course, but now we have reduced the general consensus to binary consensus. So a huge reduction. So we went from arbitrary number of processes to two processes, and from arbitrary number of bits, essentially, to 1 bit, 2 states. Okay, so this is now the simplest possible formulation. And now I can actually give you a full state diagram of of any two-thread consensus protocol. So what does that mean? I mean, bear with me a little bit, but what we'll see is we first start with an initial state. So what is the state? A state is now the setup of all of the value of all the objects, all the variables, all the memory at each of those threads, global and local variables. So we will get to this in a couple of minutes. But basically, there's always an initial state where I have threads A and B. Well, both of them, we have these two threads. We called them 0 and 1 before, but now let's call them A and B. They have not even executed the first instruction of the consensus protocol. So this is the initialization state. Nobody has done anything. Right? This always exists. And then, depending on which thread now moves in the sequential version of this parallel protocol, there's either thread A could move or thread B could move. And they move into a new state, right? Each of those. So now you could say, well, actually from every state, I get to at most 2 different states, Because each of those threads executes a sequential program. So it's either that thread A executes the next instruction or thread B executes the next instruction. There's nothing else that can happen because they have their local instruction counter. So, which means the state diagram that we see here is always a binary tree. Okay, that makes it relatively simple. We know what a binary tree is. We also know that there must be a final state after we have traversed the whole state diagram, after threads A and B moved and moved and moved and moved and moved and moved and moved. And that final state must be a decided state. So it's either 0 or 1, the output of that state. Right? And this is what we draw here with a 0 or a 1 in that circle. Well, in that case, I'm drawing a 1 here. Okay? And this also means, like what's even more important, implied by the weight freedom, this tree must have a finite size. It must have a finite height. Right? Because each of the threads must finish after a fixed number of steps, which means you cannot go infinitely deep in this tree. You have only so many steps to make for each process, and these steps are exhausted at some point, and thus there must be a finite size of that tree, of that state diagram. So this is now a little bit abstract. So what does it really mean to have these states? So let me go a little bit more into practical detail of what a state is. I mentioned the state is really all the different versions of all the different values of all objects and variables inside the program. Right? So now we have two threads, and a state now contains both of these threads state and the shared variables that are shared across the threads. So I have thread local variables of A, I have thread local variables of B in addition to the shared state, and then of course I have a program counter for both A and B because they can be different. And now if I'm looking at two different states, two potentially different states, right? I can look at, for example, the shared variables here. So let's say there's an R1 equals 3, R1 equals 3 in both cases. So in state 1, I'll call the state 0, and state 1, they both have the same value. The thread local variables of process B, you can see, are basically the same. It's y equals 0. The program counter of process B or thread B is also the same. So somehow from thread B's perspective, S0 and S1 look exactly the same. Well, that's interesting. But now they could still be different, because now I have a different thread, thread A, where I, for example, have thread A local variable x equals 2, and in the other state x equals 1. And the program counter could also be somewhere else. So thread A would be able to distinguish state 0 and state 1, but thread B would not be able to distinguish state 0 and state 1. This is a very interesting observation, and we're going to use this observation in the explanation of the proof, or in the proof itself, not just the explanation. Okay, so this is basically what I just said. The states are different, but only, so they're generally different, but only thread A can tell that they're different, thread B cannot tell. Right? So we know they are different because we see both A and B, but the threads themselves, they don't see it. Okay. Very important. So thread B does not really know, unless A tells thread B. So how can thread A tell thread B? Well, it could just write it into a shared variable. That's one of the ways that you can learn about the state of a different process. It's actually, in our model, it's kind of the only way you can learn about it in our shared memory model. Okay, so now let me go a little bit more into detail of the valency. So if we have a two-thread consensus protocol here, a binary two-thread consensus, these threads either decide 0 or 1. So which means at some point during the execution, each of those threads will decide, and this is what the routine is called, what to return. Right? So now we introduce some terminology. We basically decide a state that is that has decided on a 1 as an output value, 1 valent, and as a 0, 0 valent. Okay. We also have so-called Bi-Valence states, which means the state is not decided what to return, like either 0 or 1. Right? So we also call these 0 valent and 1 valent states. Both of those are called univalent because they have one decision already made. So they have one valency value already fixed. So for example, in this example here, the initial state is bivalent because it could be 0 or 1 as an output. And actually, this generalizes for any consensus protocol you can construct. The initial state must always be bivalent. Excuse me, for any binary two-thread consensus. right? Because otherwise bivalency makes no sense, at least only in the sense of binary protocols. And now I can give you a quick proof outline. It's relatively easy to understand, but I give you a proof by example for here. So consider the initial state where A has an input 0 and B has an input 1. Okay, so that's one particular way to run the consensus protocol. So now we could choose a scenario where A finishes before B starts, which means, because it's weight free, right? A must be able to finish before B starts, which means we must decide 0 in that case. Okay, sure. But if now B finishes before A starts, in that other case, which is still the same setup, but just a different execution order of these threads, right? We must decide 1. And now it's pretty obvious that if in one execution we must decide 0, and in or history, you could call this history as well, to connect it back to what we had in the lecture, and in another execution we must decide 1, then the initial state cannot be pre-decided. Right? It must be bivalent. It must allow the decision of 0 and it must allow the decision of 1. Okay? So furthermore, there is a little bit more of a definition coming here. There is the concept of a critical state. So we know that there is at least one bivalent state in each of those executions. So this is an execution. Remember, this is an execution tree. Like we move from state to state to state. The left side is executing one thread. The right side is executing another thread. Like if we go left or right, that's this binary tree that we talked about before. The initial state is always bivalent. That's what we just proved. That is just necessary. So now let me introduce a new terminology that's called a critical state. And we have it up here. A bivalent state is critical if both child states, remember each state has 2 child states depending on which process moves. Oh no, most states have 2 child states. Some may only have 1. If both child states or all child states are univalent. Okay? So the outputs are always univalent because by the time we reach the leaves of the tree, we must have made a decision. It's the consensus definition, right? So we have exhausted our steps to be weight free, and we must have made a decision. So the output states are univalent. So somewhere in the middle from the input state to the output states, we have to make a decision here. And then there are these critical states where you force the threads to make a decision. So at some point there must be such a state. So it's kind of intuitive. So, for example, if we go backwards, if we have these 2 states here, it's like 1, 1, it's pretty clear that if I'm here, I've already made a decision because there's no different outcome. So even that parent state is univalent. Okay? But now if I'm looking at this state, for example, I could either decide 0 or I could decide 1, depending on which thread moves. So which means this state is still bivalent. But we also see that this state here is actually a critical state because both of his successors, this one and this one, are univalent. So this is called a critical state. We see that this state is not a critical state because only the left successor is univalent, the right successor is bivalent. Right? We also see that this state is not a critical state and this state is also not a critical state. Okay, so now to understand this a little bit better, let's go through some quiz for you. So I will give you a little bit time. Sorry, it's not interactive in this case here. Usually I would make it interactive, but I'll give you a little bit of time how to name these states. So is this a univalent or bivalent state? Think about it. It's of course univalent because all output states are univalent. So let's not go into too much detail. It's also univalent here. So each of these output states are univalent. So now let's move up to this state. So is this a univalent or bivalent state? And is this critical or not? Well, it is bivalent because you can reach 0 and 1. And it is also critical because both of these children states are univalent. Okay, so let's talk about this state here. Well, this is the initial state. It's bivalent, of course, because the initial state is always bivalent, as I proved, but it's not critical because this state here is not univalent, right? It had this 0 or 1. Okay. So then what about this state? Is this bivalent or univalent, and is this critical or not? Right? And you can easily see state is bivalent and it's not critical because there's another bivalent state here. Okay, so this just as a quick exercise. So now as an existence proof, I can now give you the lemma 2. Like the first lemma was that the initial state is always bivalent. The second lemma here is that that we are going to need later is that every consensus protocol has a critical state, at least one. Okay, that is somewhat intuitive, and the proof is also somewhat intuitive because we are starting at a bivalent start state. So now let's just move the protocol, like let's traverse the state tree in a way that we only move to bivalent states. Right? We move from state to state and we try to only move to bivalent state. And once we cannot move to another bivalent state, we are at the critical state, right? By definition. But we know that the tree is of limited size because of this weight free, right? So it cannot run forever. So which really means it must reach a position where it cannot move anymore into a bivalent state and only into univalent states, and this is the critical state, so we are done. Okay? So this is a very simple, very, very simple proof. Okay, so a little bit more in detail. So assume we have the critical state. We are in some critical state here. Right? So this is now not the root of the protocol. This is a bivalent state that is also a critical state. So the question is now, what can happen if A moves or if B moves in order to make a decision? Right? So assume now that if A moves first, we go to 0, we decide 0, just without loss of generality. And if B moves first, we decide 1. And if you don't like this, you can just switch it without loss of generality. So now is the question, what actions, like in these clouds here, can thread A or thread B do or perform in order to make its move in order to make the decision? So it has exactly one action to make the decision because we're in a critical state. It cannot take multiple actions. So what is this one action that is going to take the decision for A or B? Right? This is now the question. So of course, it has to be either reading or writing a shared register. Right? So if that is not clear, let's just assume we are again in our critical state. And now thread A, who's supposed to make a decision here, does only local operations, like it updates x, y, and z, and all of them are local. For example, it says x equals y plus z, and then it makes a decision to go to 0. Yeah? Okay. So there's another question. What happens if A just reads from and writes to local variables? Well, as we know, if we are in this left side, here, this reading local variables must make a decision to go to 0. And on the right side, if B moves first, it must make a decision to go to 1, right? Because this is what we defined before. Okay. But now, we can always just say, well, if we are in this state here, we pause thread A forever, or for a very long time, and then B runs solo to the end. Of course, if we are in this output must be 0 case, then B must decide 0, even though A is never invoked again. And this is the key of this proof. Which means this is the critical step, but then A is not invoked again, and B runs to the end, and B must decide 0. So now it's obvious to you that this can either not be the critical step, because B cannot observe what A has done locally. Right? A just disappeared now forever. So meaning that this cannot be the operation that makes a decision, because it's not observable by B. B would not decide 0, B would decide 1, or could not know what to decide, in fact. Right? So this is kind of the critical piece here. So in other words, from B's perspective, these two states, like this state 1 and this state 2, look exactly the same, right, as I showed you earlier. B cannot distinguish these two states, but in state 1, B needs to decide 0, and in state 2, B needs to decide 1. This does not work, so basically conclude that the first instruction after a critical state must be a read or write of a shared variable, because if I'm only reading local variables, I will not be able to do this, to make a decision, right? Which is clear because the other thread does not see any reads or writes to local variables of my local piece. Okay, so we now know that reading or writing local variables cannot leave a critical state, right? So it must remain in the critical state because you cannot learn anything about the... So these operations are not valid operations after a critical state. They don't leave the critical state. So now the question is, what can we do if A moves or if B moves? And it must now read or write shared variables. Like this. By the way, with these registers, the only thing you can do is reading or writing. So this is our universe, is reading and writing. Now we excluded reading and writing local variables. Now we move to reading and writing shared variables. So we have two steps to make. So either A can read a shared variable, or A can write a shared variable, or B can read the same shared variable, or B can read a different shared variable. Now it comes the enumeration, as you can see. Or B can write the same shared variable, or B can write a different variable. So these are a whole lot of different options that we have. And I think these options are best arranged into a table, so that we can understand them and we see them in one go. What are the options for A's move and for B's move? Because as we are in this state, either A or B's move, both of them, each of them, need to move to the critical, need to move to a univalent state. Otherwise it wouldn't be a critical state. Okay, so let's look at a table of what happens. So we have here the first action and the second action. And here the first action, here the first action and then here the second action. Basically the same table with first and second swapped. So we could now look at all these combinations. So the first action is A reads R1. And the second action is B reads R1, or B reads R2, or B writes R1, or B writes R2. And then the first action accordingly could be A reads R2 or writes R2, and then all the combinations of these reading and writing R2 and R1. So these are 16 combinations total, 4 by 4, because we have 2 registers and 2 options for each. So 2 to the 4. And then of course we can swap first and second action, and then we get to the second table down here. So now the question is, can we simplify this? Because it's binary consensus. And this is where we now use the simplification we have employed earlier. And the first simplification we can do is actually, well, we just define that A always moves first. And if A doesn't move first, we switch names. So again, we introduce this without loss of generality principle, where we basically say, well, just let's call the first mover A and forget about the second table. So we're down to 16 options, right? This is the simplest. What we now also can do, we can apply the same principle and say, well, let's now call the first read the first read of thread A, let's now call this R1 in both cases. Sorry, I got confused. So whatever A reads first is called R1. If this is not the case, we just swap the two names again, right? So we can eliminate half of that table immediately. Right? So now we are down to only 8 options. Right? And this is somehow looks more manageable. And now we can now look separately at the cases where A reads. So we have now by symmetry excluded 3/4 of these options. You can now construct the same argument for each of these 3 missing quadrants that you want here by renaming things. So we just don't do this explicitly, but you could do it if you wanted. We call this without loss of generality. Right? Okay. So impossibility proof for case number 1 is now where A reads. Okay, so we now are in our bivalent state. And now we can say A reads something and B does something else. I mean, X really means anything. Right? And now remember the definition of the critical state, critical bivalent state, is that here output is decided as 1 and here output is decided as 0. But now what we do again is this assumption that we made before, that here at this point kind of A disappears, so sleeps, and then B continues doing whatever B wants to do, but B still has to decide 0 in this case. Right? So the problem is now that if this operation here is A reads something, then A does not modify shared state. So it's exactly the same as we had before, that from B's perspective, these two states, let's again call them S1 and S2, are actually exactly the same. But B, now like before, needs to output 0 in S1 and 1 in S2. So this does not work. So basically, which is quite obvious in hindsight, that if A reads something, it cannot influence B. So B cannot make a decision based on A reading something, right? That's pretty clear because reading doesn't change anything in the system, in the state that B observes. It changes only A's state, but now A disappeared. Okay, so which means forget about all the A reads cases. So all of those are immediately excluded. So half of our 8 cases are gone because it really doesn't matter what B does when A reads. It cannot make a decision based on this. So now let's go to those other 4 cases. Can we implement binary consensus with any of those in a weight-free manner? Let's just move to the somewhat obvious next case by renaming A and B and say, well, you know, what if B reads something instead of A reads something, and then A just does X and and A does X again, and then here B sleeps or disappears. We need to decide 0 and 1, very much like before. Well, at this point, it should be obvious that from A's perspective now, these two states look exactly the same, but A now needs to output either 0 or 1, depending on whether it's in S1 or in S2. So, again, if B cannot be influenced by A reading, then A can also not be influenced by B reading. Right? That's by symmetry pretty obvious, and we now change or remove the other two, remaining half of the cases. So now we are really back to 2 remaining cases that are interesting. And these cases are A writes register 1 and B writes register 1, or A writes register 1 and B writes register 2, because we excluded all the cases where 1 reads. Right? Remember, it's quite important here to have the state defined as a critical state, right? Because otherwise you would of course be able to make other updates later, but no, you have to make the decision in this state. So with read, you cannot make a decision, right? That's really important to understand. Okay, so now let's look at case number 2 that I just chose to be A and B write to different registers. So now we have the bivalent state, the critical state again here, where A writes to R1 and B writes to R2. But of course, this is now, here we have to output 0, and here we have to output 1. But what is then left to be done, because both of them write, is that it's just the order of writes are different. So here B writes to R2 and then A writes to R1. And now, since they're writing to different registers, the state that they end up with is irrespective of the order of writing. Right? It doesn't matter if I'm writing R1 first and then R2, or R2 first and then R1. The state at the end is both R1 and R2 have been updated with the respective values of A and B. So this state, let's call it S1, is indistinguishable from both A's and B's perspective from the left side, whether it comes from the left side or from the right side. But unfortunately, we said that the decision must be made here at this, in this instant here, to either go to 0 or 1. So you cannot end up in the same state again, but you do if you execute these both of these write operations. So, because on the left side you need to output 0, and on the right side you need to output 1, and state S1 is indistinguishable. So that cannot work. That is impossible. Which in other words is also in hindsight relatively obvious, because if both of them write, and if both of them must succeed with a write to different values, well, then the order does not matter. Then they cannot make a decision by writing in, if the order does not matter, cannot make a decision by writing to these variables. So, but now the last option that we have left is I write to the same register. Okay, wouldn't that be? And that sounds kind of interesting, right? If they write to the same register, then you could say, well, the one that writes last wins, or something like that. Right? This is very often the principle in parallel or shared memory programming, the one who writes last or the one who writes first wins, and then you decide this way. But we didn't make that consideration with our weight freedom in mind. So this would work if it was not weight free. But since it's weight free, any of these threads can at any time disappear for long enough that the other thread must finish its operation. So now we are going back to a case we already had in a very similar form. So we have our bivalent critical state, right? We need, by A writing to R, we need to get to the 0 decision state, and by B writing to R, we need to get to the 1 decision state. And now invoking our weight freedom, A goes again sleeping, and this is always where the weight freedom comes in, and B now is forced to make progress, right? So it cannot wait for A coming back. Right? That's the important piece. So B now must make progress, but unfortunately B's operation is to write R. Right? So then we have again state 1 and state 2. And since B just overwrote what A wrote before it disappeared, well, there is no difference between these two states, S1 and S2 again, and B cannot decide 0 in S1 and 1 in S2. So we have again the same problem, that these states are indistinguishable, and this does not work. So now we proved by, without loss of generality, application going down from these 4 quadrants to 1 quadrant. We proved by excluding all reads that they cannot change, that they cannot make a decision by reading, and we showed the 2 remaining write cases, either the same register or different registers, can also not make a decision in weight-free binary consensus. So it's quite constrained. You can in fact make decisions if you lift the weight freedom, for example, if you would just wait for one thread, if you would introduce a fixed order. But since we are working on weight-free here, that would not work. And this is also, and this was actually many of these proof techniques, this valence argument was borrowed from a very famous result, the impossibility of distributed consensus with one faulty process. You can prove similar things in distributed systems. I already told you that this will come back to you if you choose distributed systems, or even operating systems follow these principles. It's very much the same or very similar proof methodologies with these valence argument. So even if you don't necessarily need this particular result, the weight freedom result here, you can use that proof technique that I just applied in many, many different contexts. So it's quite powerful. And with that, I would like to finish my bonus lecture, and I hope you enjoyed it, and hope to see you later in some lecture again. Thank you.